Determining whether a radiation treatment room falls under the definition of a patient care area is crucial for ensuring electrical safety and code compliance. The National Electrical Code, or NEC, defines patient care areas in Article 517, specifically addressing electrical systems in healthcare facilities. A patient care area is any portion of a healthcare facility wherein patients are intended to be examined or treated. This definition is broad and encompasses various settings within a healthcare environment. For radiation oncology clinics, the treatment room is undoubtedly a location where patients receive treatment, thus placing it squarely within the definition of a patient care area. NEC 517.13 outlines specific requirements for wiring methods in patient care areas to minimize the risk of electrical shock. This section mandates that the grounding system in these areas must provide a low impedance path to ground, reducing the potential for voltage differences between conductive surfaces. Compliance with 517.13 is essential to safeguard patients and healthcare personnel from electrical hazards. Regarding the conduits under the slab, the question of whether they need to comply with 517.13 depends on their location and the type of wiring they contain. If the conduits are located within a patient care area and contain electrical conductors serving equipment used for patient care, they generally fall under the purview of 517.13. This requirement stems from the need to maintain a robust grounding system throughout the patient care environment. Now let's examine the use of electrical metallic tubing, or EMT, under the slab. NEC 358.10b permits the use of EMT in concrete slabs and direct burial in earth, provided it is suitably protected against corrosion. However, the suitability of EMT for underground applications is a matter of practical experience and local environmental conditions. EMT is typically manufactured from galvanized steel, which provides a degree of corrosion resistance. Nevertheless, prolonged exposure to moisture, corrosive soils, and chemicals can degrade the galvanization and lead to rust. The durability of EMT in the earth depends on several factors. Firstly, the composition of the soil plays a significant role. Soils with high levels of acidity, chlorides, or sulfates can accelerate corrosion. Secondly, the presence of moisture is a major contributor to corrosion. Continuously wet or damp soil will create a more corrosive environment than dry soil. Thirdly, the quality of the EMT installation can influence its longevity. Proper jointing, support, and protection against physical damage are essential for preventing premature failure. To enhance the corrosion resistance of EMT in underground applications, several measures can be taken. Firstly, consider using supplementary corrosion protection. This might involve applying a coating of bituminous paint or wrapping the EMT with a protective tape designed for underground use. Secondly, ensure that all EMT fittings are properly tightened and sealed to prevent moisture ingress. Thirdly, provide adequate drainage to minimize water accumulation around the conduit. Fourthly, backfill the trench with a material that is non-corrosive and provides good drainage, such as clean sand or gravel. Alternatives to EMT for underground applications include rigid metal conduit, or RMC, rigid polyvinyl chloride conduit, or PVC, and intermediate metal conduit, or IMC. RMC offers superior corrosion resistance compared to EMT due to its thicker walls and heavier galvanization. PVC conduit is inherently resistant to corrosion, making it well suited for underground environments. IMC provides a compromise between EMT and RMC in terms of cost and corrosion resistance. When selecting a conduit material for underground use, consider the specific conditions at the site. Conduct a soil analysis to determine the presence of corrosive elements. Evaluate the level of moisture and the potential for water accumulation. Consult with a qualified electrical engineer or contractor to determine the most appropriate conduit type for the application. Furthermore, when running power conductors, free air from the pit up into the equipment, proper support and insulation are critical. The conductors must be adequately supported to prevent stress on the terminations. The insulation must be suitable for the voltage and temperature rating of the conductors. Additionally, consider protecting the conductors from physical damage by enclosing them in a suitable raceway or guard. Regarding specific NEC requirements, several sections are relevant to the installation of electrical systems in radiation oncology clinics. NEC 517.10 addresses the general requirements for electrical systems and healthcare facilities, emphasizing the importance of reliability and safety. NEC 517.11 covers the essential electrical systems, which are designed to provide power during interruptions of the normal power supply. NEC 517.13, as previously mentioned, outlines the requirements for grounding in patient care areas. NEC 517.19 addresses the requirements for critical care areas, which may apply to certain portions of a radiation oncology clinic. NEC 517.20 covers the requirements for wet locations, which may be relevant if the treatment room includes hydrotherapy equipment. NEC Article 660 provides requirements for X-ray equipment. Ensuring compliance with these NEC requirements is paramount for protecting patients, healthcare personnel, and the facility itself. Failure to comply with the code can result in electrical hazards, equipment malfunctions, and potential legal liabilities. Therefore, it is essential to engage qualified electrical professionals who are familiar with the NEC and have experience in healthcare facility electrical installations. The design and installation of electrical systems in radiation oncology clinics are complex and require careful attention to detail. It is important to consider all relevant factors, including the definition of patient care areas, the requirements for grounding, the suitability of conduit materials for underground applications, and the specific NEC requirements for healthcare facilities. By adhering to these guidelines, it is possible to create a safe and reliable electrical system that supports the delivery of high-quality patient care. In summary, firstly, determine if the radiation treatment room is defined as a patient care area under NEC 517. Secondly, assess if the conduits under the slab fall under 517.13 requirements based on their location and the conductors they contain. Thirdly, evaluate the soil conditions to determine if EMT is suitable for underground use, considering corrosion potential. Fourthly, consider supplementary corrosion protection measures for EMT, such as coatings or wrappings. Fifthly, explore alternative conduit materials like RMC, PVC, or IMC for improved corrosion resistance. Sixthly, ensure proper support and insulation for power conductors running free air. Seventhly, consult with qualified electrical professionals for expert guidance and code compliance. Eighthly, adhere to all relevant NEC articles, including 517.10, 517.11, 517.13, 517.19, 517.20, and Article 660. Ninthly, prioritize patient and personnel safety in all electrical design and installation decisions. Tenthly, maintain detailed documentation of all electrical work for future reference and inspections. Consider the specific equipment being installed. Radiation equipment often has very specific electrical requirements. A licensed, qualified professional engineer should design the electrical system for the equipment. The equipment manufacturer will provide the electrical requirements. These requirements should be incorporated into the design and verified during the installation. When selecting the type of wiring to use, always be sure it is rated for the location. For example, if the location is damp or wet, the wiring must be rated for wet locations. The same applies for temperature. If the wiring is exposed to high ambient temperatures, the wiring must be rated to handle that temperature. The ampacity of the wiring must also be considered. The wiring must be properly sized to handle the load it will be carrying. If the wiring is too small, it could overheat and cause a fire. Consider the grounding and bonding of the equipment. All equipment should be properly grounded and bonded to ensure that it is safe to operate. This will help to prevent electrical shocks and other electrical hazards. The grounding and bonding system should be designed and installed by a qualified electrician. Consider the overcurrent protection of the equipment. All equipment should be protected by overcurrent protection devices, such as circuit breakers or fuses. These devices will help to protect the equipment from damage in the event of a short circuit or overload. The overcurrent protection devices should be sized and installed by a qualified electrician. The location of the equipment must also be considered. Is the equipment located in a hazardous location? If so, the wiring and equipment must be rated for that type of location. Hazardous locations are defined in the NEC. The NEC provides specific requirements for wiring and equipment in hazardous locations. Consider also the need for emergency power. Radiation equipment is critical equipment, and it may be necessary to provide emergency power to the equipment in the event of a power outage. The emergency power system should be designed and installed by a qualified electrician. Consider the need for a separate grounding electrode system. In some cases, it may be necessary to install a separate grounding electrode system for the radiation equipment. This will help to ensure that the equipment is properly grounded and bonded. A separate grounding electrode system should be designed and installed by a qualified electrician. Consider the need for surge protection. Radiation equipment is sensitive equipment, and it may be necessary to provide surge protection to the equipment to protect it from damage from power surges. The surge protection system should be designed and installed by a qualified electrician. Always follow the manufacturer's recommendations for the installation of the radiation equipment. The manufacturer's recommendations will provide specific information about the electrical requirements for the equipment. The manufacturer's recommendations should be followed closely to ensure that the equipment is installed properly and safely. Consider using a checklist to ensure that all of the necessary steps have been taken. A checklist can help to ensure that all of the necessary steps have been taken during the installation of the electrical system for the radiation equipment. The checklist should be created by a qualified electrician or engineer. Remember to document all of the work that has been done. It is important to document all of the work that has been done during the installation of the electrical system for the radiation equipment. This documentation will be helpful for future maintenance and repairs. The documentation should include drawings, specifications, and test reports. The ampacity of conductors is a critical factor in electrical installations. Ampacity refers to the current carrying capacity of a conductor, and it is determined by factors such as conductor size, insulation type, ambient temperature, and installation method. The NEC provides tables that specify the ampacity of various conductors under different conditions. These tables are essential for selecting the appropriate conductor size for a given load. For example, NEC Table 310.16 provides ampacity ratings for insulated conductors rated up to 600 volts, installed in race WISO cables, and based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds 30 degrees Celsius, a correction factor must be applied to the ampacity rating. Similarly, if the conductors are installed in a manner that restricts heat dissipation, such as when multiple conductors are bundled together, a dirting factor must be applied. Voltage drop is another important consideration in electrical installations. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized appropriately. Larger conductors have lower resistance and therefore result in less voltage drop. The length of the conductor also affects voltage drop. Longer conductors will experience greater voltage drop than shorter conductors. Ground fault circuit interrupters, or GFCIs, are essential safety devices that protect against electrical shock. GFCIs monitor the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 mA or more between the current in the hot and neutral conductors, the GFCI will trip, interrupting the circuit and preventing electrical shock. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. In healthcare facilities, GFCIs are often required in patient care areas to protect patients and healthcare personnel from electrical hazards. Arc fault circuit interrupters, or AFCIs, are another type of safety device that protects against electrical fires. AFCIs detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when insulation on wires becomes damaged or when connections become loose. When an offside detects an arc fault, it will trip, interrupting the circuit and preventing a fire. SIs are typically required in bedrooms and other areas where people sleep, as these are the areas where electrical fires are most likely to occur. Transient voltage surge suppressors, or TVSSs, protect electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. TVSSs divert the surge current to ground, protecting the equipment from damage. TVSSs are often installed at the service entrance of a building to protect the entire electrical system from voltage surges. They can also be installed at individual pieces of equipment to provide more localized protection. Electrical panels must be properly labeled to identify the circuits they serve. Clear and accurate labeling is essential for safety and for troubleshooting electrical problems. The label should indicate the type of load served by each circuit, as well as the location of the load. The labeling should be durable and resistant to fading or damage. It should also be easy to read and understand. In healthcare facilities, the labeling should be particularly clear and concise, as healthcare personnel may need to quickly identify and to energize circuits in emergency situations. Electrical inspections are an important part of ensuring electrical safety. Electrical inspections are conducted by qualified electrical inspectors who examine electrical systems to ensure that they comply with the NEC and other applicable codes. Electrical inspections can identify potential hazards and ensure that electrical systems are installed and maintained properly. Regular electrical inspections can help to prevent electrical fires, electrical shocks, and other electrical accidents. In healthcare facilities, electrical inspections are particularly important due to the sensitive nature of the environment and the potential for electrical hazards to affect patients and healthcare personnel. Electrical systems in healthcare facilities should be inspected regularly to ensure that they are safe and reliable. Proper maintenance of electrical systems is essential for ensuring their safety and reliability. Electrical systems should be inspected regularly for signs of wear and tear, damage, or corrosion. Any problems should be addressed promptly to prevent them from escalating into more serious issues. Maintenance tasks may include tightening connections, replacing damaged wiring, cleaning electrical panels, and testing safety devices such as GFCIs and FSIs. A qualified electrician should perform all electrical maintenance work. Training is essential for anyone who works on or around electrical systems. Electrical workers should receive comprehensive training in electrical safety, NEC requirements, and proper work practices. Training can help to prevent electrical accidents and ensure that electrical work is performed safely and correctly. In healthcare facilities, training is particularly important for healthcare personnel who may need to operate or interact with electrical equipment. Healthcare personnel should be trained on how to recognize electrical hazards and how to respond in emergency situations. Coordination studies are performed to ensure that overcurrent protection devices are properly coordinated. Coordination studies involve analyzing the electrical system to determine the appropriate settings for circuit breakers and fuses. The goal of a coordination study is to ensure that the overcurrent protection devices will trip selectively, meaning that only the device closest to the fault will trip, minimizing the impact on the rest of the electrical system. Coordination studies are particularly important in healthcare facilities where it is essential to maintain power to critical equipment and systems. A properly coordinated electrical system can help to prevent widespread power outages in the event of a fault. Short circuit studies are performed to determine the magnitude of fault currents that can occur in an electrical system. Short circuit studies involve analyzing the electrical system to determine the maximum fault current that can flow at various points in the system. The results of a short circuit study are used to select overcurrent protection devices that are capable of interrupting the maximum fault current. Short circuit studies are essential for ensuring that the electrical system is protected from damage in the event of a short circuit. Arc flash studies are performed to determine the potential arc flash hazards in an electrical system. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit or other electrical fault creates an explosive release of energy. Arc flash can cause serious burns, injuries, and even death. Arc flash studies involve analyzing the electrical system to determine the potential arc flash incident energy at various points in the system. The results of an arc flash study are used to determine the appropriate personal protective equipment, or PPE, that electrical workers must wear when working on or near energized electrical equipment. Arc flash studies are also used to develop safe work practices that can minimize the risk of arc flash incidents. The design of electrical systems for radiation oncology clinics requires a thorough understanding of the NEC, as well as specialized knowledge of radiation equipment and healthcare facility requirements. A qualified electrical engineer with experience in healthcare facility electrical design should be involved in the design process. The design should address all relevant factors, including patient care area requirements, grounding and bonding, overcurrent protection, voltage drop, and coordination. The design should also comply with all applicable codes and standards. Commissioning is the process of verifying that an electrical system has been installed and is operating correctly. Commissioning involves testing and inspecting the electrical system to ensure that it meets the design requirements and that it is safe to operate. Commissioning should be performed by qualified commissioning agents who are independent of the installation contractor. Commissioning is an essential step in ensuring the safety and reliability of an electrical system. Ongoing monitoring of electrical systems can help to identify potential problems before they escalate into more serious issues. Monitoring can involve tracking voltage, current, temperature, and other electrical parameters. Monitoring can also involve performing regular inspections and tests to check the condition of electrical equipment. The data collected from monitoring can be used to identify trends and predict potential failures. Emergency plans should be developed for responding to electrical emergencies. Emergency plans should outline the steps to be taken in the event of a power outage, electrical fire, electrical shock, or other electrical emergency. Emergency plans should be readily available to all personnel who may need to respond to an electrical emergency. Emergency plans should be reviewed and updated regularly to ensure that they are current and effective. Security measures should be implemented to protect electrical systems from unauthorized access. Electrical rooms and panels should be secured to prevent unauthorized personnel from tampering with the electrical system. Security measures should also be implemented to protect electrical systems from cyber attacks. Cyber attacks can disrupt the operation of electrical systems and cause serious damage. Sustainability considerations should be incorporated into the design and operation of electrical systems. Energy-efficient lighting, equipment, and controls can help to reduce energy consumption and lower operating costs. Renewable energy sources, such as solar panels, can also be used to power electrical systems. Sustainability considerations can help to reduce the environmental impact of electrical systems. Collaboration between different disciplines is essential for successful electrical projects. Electrical engineers, architects, mechanical engineers, and other professionals should work together to ensure that the electrical system is properly integrated into the overall building design. Collaboration can help to identify potential conflicts and ensure that the electrical system meets the needs of all stakeholders. The information provided is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with qualified professionals for specific guidance on electrical design, installation, and maintenance.